Hello there! This lesson is all about the periodic table and the elements it contains. So this is a periodic table similar to the one that's hanging in many of your classrooms. And you'll see that it has a bunch of letters all over it, and that represents the different elements. You'll notice that there's some different colors. The colors represent the state of those elements under standard conditions. So all these red guys here, these are all gases under normal conditions, including hydrogen over here. There are a couple blue ones. Blue ones are liquids under normal conditions, standard conditions. The black ones are all solids. And the ones that are sort of hollow, those are not found in nature. So those are only if you make them in a nuclear reactor, can you get a chance to have a look at one of those, because they are unstable and do not survive on their own for any length of time. So just as a reminder, elements are made of atoms all of the same type. They all have the same type of atom. And that makes them the simplest substances that we have, the simplest form of matter. There's a few that you're probably familiar with or heard of before. This one's carbon. Carbon's always sort of a black, brittle powder or chunks. This is sulfur, very similar. Down here, I believe we have some potassium, which is a metal that you can cut with a knife. This is copper. And these signs here are made with gases like neon. Call them neon signs. I'm not sure if the yellow one is actually neon gas, but this reddish orange one, the breakfast part, that's definitely neon. So neon and all these other elements, whether they're gas or solid, can't be broken down by physical or chemical means into any simpler substance. You could break them down into electrons or protons, and you'd have sort of plasma, but that wouldn't be an element anymore, and you can't do that by physical or chemical means. So on the periodic table, there are symbols to represent the elements, sometimes the names, but always the symbols. So the symbols are usually the first two letters of the element name, or sometimes doesn't have to be the first two letters, usually the first letter and maybe some other letter that goes along with the rest of the name. So helium is a nice simple one, gets the symbol He. Lead comes from the Latin name for lead, which is plumbum. Bum. Right, so you got the P from plum and the B from bum, and so that's where the symbol for lead comes from, but the English name, of course, is lead. Tin is the same thing. The Latin for tin is stannum, and it gets the symbol Sn. But most of them come from English names, like Al is aluminum. You'll get used to a few of them that come from older languages like Latin. So when you group together all the elements that have been found, you find there are basically three main categories that you can throw them into, just from looking at them superficially. One is metals. There's a whole bunch. The majority of the periodic table is metals, and metals, of course, all have same basic properties. You can bend them and mold them. They're kind of shiny, and you can they're good conductors of electricity. Then you have a group that basically has the opposite set of characteristics. So good old sulfur again here is not very shiny, and it's not very malleable, and it doesn't conduct electricity. It's pretty much the opposite of everything there. And there are lots of other elements that are nonmetals as well that aren't even solids under normal conditions. So if you think of things like oxygen, that would definitely not be a metal because it is, it's a gas, and of course it's not going to have any of those other properties. And in between, we have a few substances that have properties of both. So this here is silicon, and it's called a metalloid because it can be conductive electricity if it's the right temperature. You can see it's a bit shiny. But also, if you hit this with a hammer, it's not going to dent like a metal would. It'll shatter, it'll break into bits like the sulfur above. So it has some characteristics of metals, but not all. So So that's why you call it a metalloid, and there's a handful of elements on the periodic table that are sort of in between and have properties of both. So this is silicon, and this here is gold, and in between we have here sulfur. Okay. So as more and more elements were found, scientists started to look for patterns, look for ways in which they could group the elements. And so many scientists, this guy John Newland, this guy Julius Mayer, and Dmitry Mendeleev, they found that they could find patterns in the elements that they had by arranging them in order of increasing mass. So the heavier they were, you put the light ones at the beginning, put the heavier ones at the end, and you start to see patterns as you go along that repeated at sort of regular intervals. Mendeleev gets the credit for coming up with the first periodic table because he left spaces for elements that didn't fit the patterns that he had. And so he predicted elements that hadn't been discovered yet just by arranging elements that did have similar properties in the same columns. And so since whenever he didn't have an element that fit the bill, he just left a space. And so that was his sort of brilliant move. And even in his own lifetime, some of those elements were discovered, and some of the properties that he predicted were found to be close to accurate. So the modern periodic table that followed after Mendeleev and others had discovered enough elements to complete the table is slightly different than Mendeleev's. It still mostly goes in order of mass, but what they found was that atomic number worked a lot better than mass for a few instances as far as the properties go. A good example might be here with tellurium and iodine. So we have the atomic mass, this is 127.6 for the tellurium, and iodine is 126.9. So that's a decrease in the mass. And yet iodine, with its properties, better fit in the column with fluorine and chlorine and bromine than it did over here. And so Mendeleev even saw this problem when he was making his table. He just thought the numbers weren't accurate. But it turns out the numbers were accurate. It's just that atomic number makes more sense, and we'll learn why later on. But our periodic table is arranged in order of increasing atomic number. So if you go from left to right, starting at the top left-hand corner, you'll see the blue numbers in the corner there. Those are the atomic numbers, and they always increase. So it's 1, 2, and then over here, 3, 4, 5, 6, 7, 8, 9, and so forth for the entire periodic table. The other piece that might be a little unusual is when you get down here to number 56, there's this section here that looks kind of wonky, and 57 is actually down here in the separate section. And this is just for aesthetics to make it fit into a sort of squarish type poster shape. If you take the actual periodic table, if you stick all of these elements in there, it ends up being kind of long and skinny, and it's not as practical to use on a piece of paper. So the numbers continue. It goes 56, and then 57 is down here, 58, 59, blah, 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 until you get to 71, and then back up here to 72, 73, and so forth. So that section belongs in there. Okay, so if you remember those different groupings of elements, the metals, the non-metals, and metalloids, it turns out if you make your periodic table with this repeating pattern thing, that those elements end up in nice, tidy groups on the periodic table. So all of your metals end up being over here on the left, metals. Down here, these are all metals. And then all of your non-metals end up being over here on the right. Non-metals, with one exception. Good old hydrogen here is a non-metal. It needs to be over there. So it's sort of out of place. And then the last bit are the metalloids. So the metalloids are the elements with some properties of both metals and non-metals. And so if you make a little staircase starting between boron and aluminum here, and just keep repeating the staircase as you go down, you'll find that all of the elements that had those mix-up properties end up being stuck to that staircase. So boron is a metalloid, silicon is a metalloid, germanium is a metalloid, arsenic is a metalloid, Antimony is a metalloid, tellurium, polonium, and astatine, all metalloids. The only exception here is good old aluminum. Even though aluminum is touching that staircase, it's totally a metal. It doesn't have any non-metal properties. But all the rest on that staircase, those are your metalloids. Maybe I'll darken that up a little bit with a different color. So there's the staircase right in there. And down. If you want to put it on your periodic table so that you can have it as a reference, that's where to put it. Okay, so the next feature of the periodic table we're going to look at is how they are organized in groups and periods. And the groups are all the vertical columns, so you see the term group there, and then the numbers 1, 2, 3, 4, etc. That's talking about these vertical columns of elements. So hydrogen down to francium, that's group 1. Beryllium down to radium, that's group 2. Group 3 is scandium and down. So all these columns down this way, these are all your groups. And then the horizontal rows are called periods. And you see the numbers here, 1, 2, 3, 4, 5. And those are talking about the elements that are in these horizontal rows going across this way, right? So if I wanted to give you the coordinates for a certain element, I could give you the group and the period, and you can tell me what element it is. So let's say if I give you group 14 and then period 3, you could go to group 14 here and go to period 3, and the place where they meet, silicon. So that's what the groups and the periods are. All right, so the first two groups we're going to look at here are groups number 1 and 2. So group 1 over here and 2 over here. This first group, if we sort of cut out hydrogen, these are all very reactive metals. If you drop them in water, they react really rapidly. Here's a couple of them over here. You got lithium and sodium and potassium. You see they're all kept under this fluid. This is mineral oil. They'll react really rapidly with water or air. And so that's how they end up in the same column. Right next door, you have what you call alkaline earth metals. So you got the alkaline metals here, and then you got the alkaline earth metals on the second column. And they're very similar. They are very reactive as well, but not nearly as reactive as that first group. You don't have to keep these ones under oil. Perhaps down lower you might, but these ones at the top anyways, you can pick up things made of magnesium or pieces of calcium. They won't hurt you. But they will react in the same sort of manner with other elements if you heat them up enough or put them under the right conditions. So that's how they all ended up in that second column. Our last two groups on the periodic table are group 17 and 18. Group 17 elements are called halogens. They are very reactive as well, but in a different way. So they all have similar reactivity to each other, and we call them halogens. Also very poisonous. And the last group are the noble gases. Now, noble gases are super unreactive. They were the last elements to be found because of their structure, they don't interact well with other elements, and it's difficult to isolate them. But there they are, and a lot of elements, because of their stable nature, when they react, end up being very similar to noble gases in that way. And we'll learn about that as we go forward. So there you go, an introduction to the periodic table, and now you know some of the features of it.